All right, guys. Welcome to this exciting YouTube lessons on chemistry. Today I'm going to be looking at electronic configuration of an atom. Okay. Now, quickly, what is the concept behind electronic configuration? Now, electronic configuration actually is the arrangement of electrons into orbitals or orbit in an atom. Okay, it's the way we arrange electrons as it's supposed to be in an atom. Okay, in the orbitals or in the shells. Okay, quickly. Now I'll quickly show you why it works. Now, quickly, let's say for nitrogen. Okay, let's say for nitrogen 14(7). Okay, we can also write it as in modern configuration. Normally write it as 714. Okay, this is how we see it in modern configuration. Okay, 714 like that. How does it work? How does it work? Now it shows that the atomic number is 7, or the atomic number is 7. So when you see the configuration, like when you see the symbol of the atom like this, or when you see the symbol of the atom like this, either way you see it, the 7 here is the atomic number. For this type, the 7 here is the atomic number. Okay, anyway, you're going to do it. Now, since there are no charge, there are 7 electrons. Now, 7 electrons, how do you configure these electrons? Okay, now how do we configure these electrons? So quickly, now there's a mechanism we have devised over the years, and you have to watch it very well. It says there are the orbits, the subshells that we have, because I'm going to be particular about subshells in this class. Now the subshells that we have are S, P, D, F, right? Okay, so according to the theory, according to our Bohr principle of building up, which I'm going to explain, first shell should have just one subshell, one S. So we don't have for these guys. For the second shell, you have 2S and 2P. For the third shell, you have 3S and 3P, then 3D. For the fourth shell, we have 4S, 4D, 4S, 4P, 4S, 4P, 4D, and 4F. For the fifth one, should have 5S, 5P, 5D. Also, there is possibility of 5F and not discovered yet. We can have 5G. Okay, we can also have a 6S, a 6P, and we have a 6D. Yeah, 6F as the case may be. So, and so on and so forth. So, but quickly, basically, let's leave it here like this. Now, let's quickly draw out the order of energy. So, this is the rule we use. Take the arrow diagonal. Yes, this is, we're going to arrange it in order of increasing energy. Order of increasing energy. So we're going to have something like this. We're going to have like this. Then we should have something like this. So if possible, there should be 7s here. Okay, like this. Now, so quickly, how am I going to write it now? So for nitrogen, 7 electrons. Nitrogen, 7 electrons. And take note, the maximum number of electrons for S is 2. The maximum number of electrons for P is 6. The maximum number of electrons for D is 10. And the maximum number of electrons for F is 14. I'm going to explain. Now, so for simple nitrogen, I can see a 1s2. The next is 2s2. Remember, we're filling 7 electrons. 7 electrons. We're going to look at 7 electrons. Now, 2s2, then 4 out of 7 is remaining 3. So after 2s, we have a 2p. 2p can take a maximum of 6, but we have 4 remaining. So just the 2p4. Just have to write the electronic configuration of nitrogen into subshells. We're going to write the electronic configuration of nitrogen into subshells. Okay? In this class, I'm going to show you how we feed those electrons into orbitals, and if possible, shells. Or we'll do that for sure in the next video. Now, this is the subshells of this nitrogen atom, like this. The simple electronic configuration. Now let's take another atom. Let's take calcium, for instance. Okay, let's say calcium. So calcium should be Ca2010, or if you write it with that convention, it should be 10Ca40. So however you want to write it, that is calcium for you. Okay, however you want to write it, calcium. So pardon, so to the 20 is 20 Ca. Yes. So quickly, what is the how many electrons are present? We're going to have okay, this is not well placed. Calcium is 20 as the atomic number 40 there. So we're going to have 20 electrons for calcium, 20 electrons. Using this convention to feed it, let's see how it's going to look like. So we should have 1s. So 1s2, 2s2, 1s, 2s. What do we go to next? 2p, this direction of the arrow. 2p6. So how many have I filled now? 2 plus 2 plus 6, that is 10. After 2p6, we go down, we have a 3s2. 2p6, 3s2. After 3s2, we're going to come here. See the direction of the arrow, we have 3p6. 3p6. Right? So this should be around 18 now. This 2 plus 6, 2 plus 2 plus 6, 10, plus 2, 12, 12 plus 6, 18. Electrons are filled 18. Now, and I'm filling 20. So 20, the next, after 3p, after 3p, I should have a 4s. So after 3p, 4s, and s can take a maximum of 2. So we have 18 already. We have fit 18 already. We have to fit 20. So we just add a 2 here. So this is the electronic configuration of calcium electrons into subshells. SPDF are subshells. Okay, if you want to know more about that, I will drop the link on this video, or the link on quantum numbers. Yes, quantum numbers. If you need, because in the video on quantum numbers, I explain the difference between shell, subshells, and orbitals. So you can go and see. So I'm just trying to fill electrons into the subshells now. Now, in that video also, if you cover that video, I said that the S has one orbital. The S subshell has one orbital. The P subshell has 3 orbitals. The D subshells have 5 orbitals. 1, 2, 3, 4, and 5. While the F subshell, I said, has 7 orbitals, where an orbital can take 2 electrons maximum. The maximum number of electrons in any orbital is 2 maximum. Maximum 2. Now, F is 2. Okay, F is 7 orbitals. So 1, 2, 3, 4, 5, 6, 7. So if you put 2 here, 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 you should have a maximum of electron of 14. So this subshell, this F subshell can take 14 electrons, but each of the orbitals takes a maximum of 2. Okay, okay, so that's that for this that's that for that. Now, I would like to show you how we fill electrons into these orbitals. I would like to show you how we fill electrons into these orbitals. This is how we just fill electrons into subshells. This is how you just assign subshells to an atom, or to the electrons of an atom. Simple. Now, before I show you this, I will use an ion, a species that is charged. So let's take SC3 plus, where you have 21 and we have 43. SC3 plus 21, 43. All right, so this is scandium ion. Scandium ion, SC3 plus. Now, 3 plus means it has lost 3 electrons. It has 21 electrons initially, but it has lost 3. So the total number of electrons here is going to be 18. So we are about to fill 18 electrons. Yes. So filling 18 electrons, how does it look like? 18 electrons. Using this rule, quickly, let's use it. Please, those of us watching this video, this is taken through the 4F. So please take note of that. Yeah, you should take note of this. It's going through that. It's going through there. This is 4G. All right. So how do you fill 18 electrons? 18 electrons. I can also use this. I'll stop here. So let's check. It's going to be, if you follow there, I'm going to use 1s. You should take 2. Next is going to be 2s. You should take 2. Next is going to be, there's no other one again. So put here 2p. 2p, it takes 6. 2p, it takes 6. After 2p, it takes 6. We're going to have 3s. 3s, it takes 2. So how many have we filled like that? 1, 2, 3, 4. Right? 1, 2, 3, 4. 1, 2, 3, 4. So 4, um, um, 4. So this is 2 plus 2 plus 6. That's 10 plus 2. That's 12. So we have to fill 18. So 3. Now after 3s2, we go to 3p6. 3p maximum of 6. Now we have 18. But I like to do it like this so you get what we are trying to say. I like to do it like this so you get what we're trying to say. Now, I will not just call this guy 18 electron. I'm going to call it, please watch. I'm going to call it 21 electron minus plus 3 electrons. 21 electrons minus plus 3. At the end of the day, we're going to have 18. But please watch something. Now, 3p6. Next, we are going to go to 4s2, making it 20. Yes, 20. It's going to be 21. After 4s2, we move to 3d. We are going to 3d1. Yes, after 4s, there's no other guy. Move to the next row, 3d. All right, so now, how do you lose 3 electrons from this kind of configuration? It is very important to write it full so that you know your exact answer. How do you lose 3 electrons from this kind of configuration? Now, after writing it like this, for losing of electron, this is for loss of electron, it is better you group these subshells. You group them. Now, when I mean group, 1s is the first shell. I group it. 2s2 and 2p6 are the second shell. I group it. Now, 3s2 and 3p6 and even 3d1 are all on the third shell. I group it. Then the last shell is going to be a 4s2. I group it. So there are 4 shells here. 1, 2, 3, 4. 4 shell. It means the third shell is taking 9 electrons. Yes. Third shell takes 9 electrons. Now, but mind you, 3d is of a higher energy than 4s, but 4s is in the outermost shell. It is chemistry. Now, how do you now lose electron? It is better you lose from the outermost shell first. So that means by losing 3 electrons, I first lose, it is easier to lose from the outermost shell first. So I'm going to lose from 4s2 first before I'm going to lose from the third shell. So if I'm to lose, I'm not going to lose electron. Let's say the final answer will now be, please watch this. It's not going to be I want to lose 4s2. Remember, I'm losing 3. So I will now have to come and lose 1 here. So that's when I'm going to lose this one. So I'm going to lose this, and I'm going to lose this. So what will that be the answer? So my answer is now going to be 1s2, okay, 2s2, 2p6, 3s2, 3p6. Yes, we got it earlier. But in some cases, the answer might not be like this. That's why not be like this. Because if you feel it like this, the question might say, please what? We say lose 2. So assuming from this configuration now, we are to lose 2. So you are going to lose from D before 4s. No. So the way if you are to lose 2, we are going to just lose only the 4s. Let's say it is SE2 plus, losing 2. We're going to lose only the 4s, leaving this configuration. It's quite interesting. All right. So moving on. So I have to write the board for some I've done earlier. I have to take it off. Yeah. Okay. I'm gonna take it off. Okay. Now let me show you how we feed these electrons into subshells. How we feed these electrons into orbitals. Pardon me, we're just doing for subshells. Okay, into orbitals. Now, when feeding electrons into orbitals, there are 3 rules we have to put in mind. The first one is our Bow's principle. When feeding electrons into orbitals, or orbitals, not necessarily degenerate orbitals, we have to look at adverse principle, I will explain. We have to look at On's rule, okay, On's rule of maximum multiplicity, and I'm going to look at Pauli's exclusion principle. Pauli's exclusion principle. All right. Now, what happens about these three principles? What's the difference? Now, our vast principle says that when filling electrons, this watch, we have to fill electrons. When filling electrons into orbitals or even subshells, we fill those with lower energy before higher energy. That's where this concept came into play. So, if you check, we are trying to classify them based on their increase in energy. That's what we're doing here. So we'll say 1s comes before 2s, and that means 1s is of lower energy than 2s, 2s is of lower energy than 2p, 2p is of lower energy than 3s, 3s is of lower energy than 3p, 3p is of lower energy than 4s, 4s is of lower energy than 3d. Yes. Well, mind you, 4 is of lower energy than 3D. I already showed you an exception. But 3D is, what's it called? 4s is in a higher orbit or in a higher shell. 4s is in the fourth shell, 3D is in the third shell. But 3D has a higher energy than 4s. Okay, now that's for our Gauss principle. What about Ohm's rule? Ohm's rule of maximum multiplicity. Ohm's rule states that when filling electrons into degenerate orbitals. The word degenerate orbital, let me explain what it said. When filling electron into degenerate orbitals from Ohm's rule, it has to do with degeneracy. Degenerate orbitals. Said when filling electrons into degenerate orbitals, we fill singly before pairing. Yes, it's fill singly before pairing. Now, what is a degenerate orbital? A degenerate orbital are orbitals that have the same energy, size, and shape. There are orbitals that usually have the same energy, size, and shape. I'll take the word the same energy and the same shape because most orbitals have the same size. Okay, the same energy, size, and shape. Okay, how do we mean? How do we mean? Now, quickly, how we mean is this. How we mean is simple. Simple. This is it. Now, once you degenerate orbitals having the same size and shape. This is what we mean. Now, for S orbital does not have another orbital that is like it. So we say S orbitals do not have degenerate orbitals. So S does not have any orbital that is like it. Now, P orbitals, this is P orbital, 3 orbitals. Now, this P orbital is similar to this P orbital. Yes, and it's similar to this P. So these 3 P orbitals are degenerate of each other. This one has the same shape as this one has the same shape as this one. So they are P orbitals have 3 degenerates. Same as D have 5 degenerates, 5 orbitals that have the same energy, size, and shape. F have 7 degenerates. So it is simple. The only orbitals that do not have the degenerate orbital is S. So the rule is trying to tell me that when filling electrons into these orbitals like this, we fill singly, yes, we fill singly before coming back to pair. That means I'm fill singly like this before coming back to pair. And the pairing is important. How do I pair? Who tells me about how I pair? Pauline's exclusion principle. Pauling says that no two electrons in the same orbital, have the same first set of quantum numbers. That at least their spin quantum number will be different for Pauline's exclusion principle. Now, so that means according to Pauline's principle, in an orbital, if one electron is a spin up, the other electron should be a spin down. That is Pauline's exclusion principle. So, having known these principles, we can quickly apply. We can quickly apply very, very fast. Very fast, we can apply. So I'm going to let you try. So I'm going to let you, I'm going to write something like, let's say, simple one. Let's say 0816, or what we can also call, if you follow, I call it 0816. So you tell me the electronic configuration. Feed the electrons into subshells for me. Into subshells. Show me my 1s, 2s. That's what I mean by subshells. Then let me do for the orbital. So we have 1 minute to do that. 1 minute. All right, so let me quickly answer that. Now, quickly answering that should be we have 8 electrons, no charge, nothing else, just one s2, two s2, two p6, three s2, and three p6. Okay, what am I saying? What am I doing? We've gone too far. So I thought it was 18, 8. So one s2, two s2, and two p3. That should be, is it 2p3? So that's 7. 2p3 is making 7, and 2p4. 2p4. Now, according to this principle, now S is one orbital. S is one orbital. S do not have degenerate orbitals, so P have degenerate. Okay, according to S and P, according to the principle I just said, we have followed Avars principle like this. Like this, feeling like this already follows Avars principle. Now, Ohm's rule is what Ohm's talking about degenerate orbitals. So Ohm's rule we're talking about somewhere here. All right, which we're talking about. So this two does not have degenerate orbital. So according to the rule, Pauline's exclusion principle, if I feel electron here, spin up, the other one should be a what? Spin down. Spin up. This should be a spin down. Now, free Pauline's exclusion. Now, according to Ohm's rule, here should be singly first before pairing. So how do you pair? Back, back, back. That's how we pair. So that's how we pair. But we have 4 electrons. 4 electrons. So filling 4 electrons should now be something like this. Filling 4 electrons now be something like this. So I should have single, 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 3, and this is the 4th one. As simple as ABCD. So this is very, very simple. So no, it's not difficult at all. These are you apply the same principle. These are the orbitals, the various orbitals. So some questions can come like this. Now the question can ask you, they ask you how many unpaired electrons are in the p orbital of oxygen? How many unpaired electrons are in the p orbitals of oxygen? Now if you check, how many unpaired electrons are there? 2 unpaired, and we have 1 paired on the p orbitals of oxygen. Pardon me. Now let me do one more example, and I'll stop the video here, and we'll take over we'll do a video on electronic configuration 2. Electronic configuration 2. Okay, that electronic configuration 2, I'm going to look at for the configuration for transition metals, and I'll talk about paramagnetism. Okay, the electronic configuration of transition metals. I'll talk about paramagnetism, diamagnetism, and ferromagnetism. I'm going to talk about the effect of having all unpaired electrons. Okay, we're going to look at heavier elements like mercury, like cardium, and so on and so forth. So electronic configuration 2. So we'll do one more example here, and we'll leave. So quickly, let's look at sodium. So I'm going to call it Na plus. Na plus. You know, Na plus has 11. Sodium has 11. 23. So this is sodium. Okay. Now, how many electrons? There are 11 electrons there initially. So the electrons are going to be 11 minus 1, as I told you to do it. So that you don't make mistake. Do it like this. 11 minus plus 1. Okay. So now let's go. Okay. Plus 1. 11 minus plus 1. So we know it's a total of 10, but solve it as 11 minus plus 1. Okay, so let's fill 11 electrons first. So 11 electrons should be 1s2, 2s2, 2p6, 3s1. That should be 11 electrons. Where here is 1 box, here is 1 box, p is 3 box, and x is finally 1 box. So this is spin up, spin down, spin up, spin down. What do we do here? Singly before pairing, there are 6. So 3, so we can take 6, pair, and you pair down, so you have 1 here. So now if you group it, if we are going to group this orbital, this is the first share group, second share group, and this is the third share. So who do we lose from? The outermost share is the third share. So who do we lose from first? We have to lose 1 electron plus 1. It means we are going to lose from the third share. So at the end of the day, we are going to lose this particular electron. So at the end of the day, losing that particular electron, I should have something like this. This is the electronic configuration of sodium ion plus 1. It has no unpaired electron. It has no unpaired electron. All the electrons are paired. So if you like this video, I know you love it, self-explanatory, try and subscribe to the video. Try and subscribe to the videos. Hit the like button, share it to your friends, your classmates, that will be useful too. Until the next video, it's a bye from us. So have a nice day, guys. See ya.